Hello, and welcome back to Marine Biology at Home. Who am I? Well, I'm Seabird McKeon, and you can reach me at thenaturalistpodcast.com or at Seabird McKeon on Twitter. I'm going to be one of your instructors for this course. There will be others. Last time we spoke, in the introduction to this series, I said that most of the world is water. And that's true. Most of the world is water. I gave you the numbers to back it up. But there is an underlying question of where did the water in the oceans come from? And it's kind of an interesting answer as well. Some of that water came from outgassing, where water vapor was expelled from the earth by volcanoes early in the history of the planet. But there's another source for the water. Some of the water came from comets that impacted the Earth. And for me, these two sources of water for our planet is a really compelling metaphor, because water is both common and ordinary and very much part of our home, part of the Earth, and it's alien. It's from somewhere else. It is playing by different rules. So, today, the theme for the lecture and the title for the lecture is that water is weird. I'll be going over some of the basic chemical and physical properties of water that allow for life on our planet. So it's important. Let's start with the water molecule, or H2O. Well, that's it right there, right? So water molecule is composed of 3 atoms, 1 oxygen atom, and then 2 hydrogen atoms. The oxygen part of this molecule is electronegative. It has a negative charge. Hydrogen, both parts, are electropositive. There are 2 types of chemical bonds holding this molecule together. So there are the covalent bonds, which are kind of your standard molecular bond. And then there's also hydrogen bonds, which are a fairly unique class. And they help us describe what is so unique about water. Many of the properties of water come from hydrogen bonds. And one of the big ones of those is what is called cohesion. So hydrogen bonds promote stickiness, and that in turn promotes cohesion. We can represent cohesion as surface tension at the air-water interface. And so that cohesive nature of water creates a film. And that film is exactly what we see things like water striders or other types of insects utilizing at the very surface as kind of a tactile boundary. So water striders make a living on this critical property of water coming from hydrogen bonds. Hopefully we'll get to water striders a little bit more deeper into the lecture series. Cohesion of water can also regulate the viscosity of water. And viscosity is a force needed to separate molecules of a substance so as to permit passage. So something like honey or syrup has a higher viscosity than water. But water does have an ability to hold itself together. There are other effects of hydrogen bonds on water, particularly when it comes to heat. So I'm going to introduce you to 3. The first of these is the heat of vaporization, which is the amount of energy required to evaporate a unit mass of a substance at a constant temperature. And the heat of vaporization is high for water due to the strength of those hydrogen bonds. And this means that water evaporates slowly and at a relatively high temperature, over 100 degrees C, and it absorbs considerable heat. The second of the effects of heat on water is what we call latent heat of fusion, or the amount of heat gained per unit mass when a substance changes from water to gas, or when it's lost, going from liquid to solid, for instance. And again, because of the hydrogen bonds, the latent heat of fusion is high for water. What does this mean? This means that to melt ice requires a lot of heat, and that forming ice gives off a lot of heat. The third effect of heat on water is what we call heat capacity. And this is the amount of energy to raise the temperature of 1 gram of material 1 degree C. So let's look at a quick chart. So here I've put up lots of common materials and their heat capacity. And we've got up here things like acetone at 0.51, and aluminum at 0.22, and ammonia at 1.13. And way down at the bottom there, we have water with a perfect score of 1 with regards to heat capacity. So I want you to take a look at this list, though, and see that other than that ammonia up there, water's really quite high. And this has major effects. This means that water is a strong buffer against rising or falling temperature. And because of that ability, it can moderate the climate. So anyone who lives near the water and in a seasonal area can tell you that the water holds temperature better than the land does. So early in the spring, the water is colder than the land is. Late in the fall, the water is warmer than the land is. And so that's moderating our climate. And it means that there's less temperature fluctuation in the water than in the air. And this has been very important for regulating the temperature of the entire planet. This buffering effect is part of what makes our planet suitable for life. Water on our planet exists in 3 states. We have liquid water that we're most familiar with, water vapor, and we have ice. And this is an interesting relationship right here. So typically, a liquid has increasing density with decreasing temperature, right? But in water, we see this general pattern playing out until about 4 degrees C. So we are reaching our maximum density of this substance at 4 degrees C. It doesn't continue to decline. Once we get to 0, we get into ice formation. And ice is actually expanding, meaning it is less dense than liquid water. So here we go. This is pretty interesting to me. And it all has to do with the hexagonal structure of the ice crystals. So if we think of ice as crystalline water, which is exactly what it is, we see an expansion. We see the 2 hydrogen atoms in that water molecule are arranged at 120 degrees. This shape creates a hexagon when grouped with other water molecules. And because of that hexagonal structure, less molecules can be packed into a specific volume. So what are the consequences of this? The consequences are that ice floats. And that by itself means that superficially frozen over habitats are still habitable. You can imagine that if ice sank when it formed, it would quickly take out most of the life left in the liquid water beneath it. So it'd either pin it to the bottom or kill it entirely. At least for the forms of life that we know right now, that would not work. So the floating of ice has had a major effect on the direction that the living organisms on this planet have gone in. Differences in water density also drive oceanic circulation. So we end up with this what we call the ocean conveyor belt, where warm, shallow currents, because the water is less dense, are up there at the top, but as they get cooler, they get slightly more dense, and they drop to the bottom. So we end up with this continuous circling cycle of currents across the world, carrying water and, to some degree, climate with it. Another feature of water that we need to be aware of before we really start digging into marine biology is how it can dissolve substances. So water is known as the universal solvent. And remember that a solvent is a fluid that dissolves a solid, liquid or gas, resulting in a solution. And that substances that dissolve in solvents are called solutes. At the very beginning of this, I told you that there's an electrical charge to the atoms of the water molecule. And so the polarity, these charges, increase the ability to form bonds with ions. And this is what makes water an excellent solvent with high dissolving power. So if we were to put table salt crystals, so NaCl, into water, we would see the dissociation of those ions into the water. So we'd end up with both sodium and chloride ions in the water. So much of the water on our planet is filled with solutes, right? So we've got total dissolved solids, and we can call this salinity. These dissolved solids are about 3.5% by weight in average seawater. And usually we express it as 35 parts per thousand. That would be 1,000 grams of seawater having 35 grams of salts. There's also a term kicking around out there called practical salinity units. And there's some variation here. Geographically because of evaporation or precipitation and rivers. The most abundant ions in seawater are chloride, sodium, sulfate, magnesium, calcium, and potassium. And together, these ions form 99.28% by weight of the solid matter in seawater. You can see that this relationship, this is going to be relatively constant, and it's really abundant. So the oceans have about 50 quadrillion, which is 50 million billion tons of dissolved salts. That means that if the salt in the world's oceans could be removed and spread evenly over the Earth's land surface, it would form a layer more than 500 feet thick. That's the height of a 40-story office building. There is a ton of salt out there. And the relationship between these ions is relatively consistent. So even when we go to different salinities of water, from 5 to 40 PSU or parts per thousand, the ratio of these major ions is similar. So that consistency between these ions means that you can determine the amount of any of the major ions by measuring one. So usually we use chloride. How do we measure salinity? Well, chlorinity is one option. We can take the grams of chloride plus or per 1,000 milligrams of seawater. And so the salinity would be 1.81 times the chlorinity. And you have to do this through chemical titration. Or we could look at conductivity. We could look at the electrical charge and how well electricity passes through water. And the conductivity increases with increasing salinity, but you have to correct it for temperature. Or we could use optical refraction. And the more salt's in the water, there's more refraction of light. And so we use this instrument that's in the picture above. It's called a refractometer. And this might be the most common way that you see people out there measuring the salinity of water. putting a few drops on a refractometer, and then letting the light pass through it and getting a measurement. So what changes the surface salinities of seawater? What processes are involved? So we've got two directions, right? We've got saltier or fresher. We've got evaporation, could make things saltier, so it's removing the water, leaving the salt behind, or precipitation, adding more water in, kind of diluting those salts. We've got sea ice formation, because the ice does not take the salts with it, leaving the remainder of the seawater saltier. Whereas sea ice melting, it's like adding more fresh water into the oceans. Same thing could be said of freshwater runoff from land, from things like rivers. They make surface waters fresher. On board ships, we can use a piece of equipment called a CTD for collecting data. And so I've given you the clues. I'm very curious. What do you think that C and T and D stand for in describing this piece of equipment? If you live in extreme northern or southern climates, you might see snow, right, on your roads. So many of us who live in these colder climates see the application of ice, or the application of salt to ice. Why would they put salt on roads? Well, it's another interesting thing about seawater is that adding salt lowers the freezing temperature of water. So that can take an icy road or a sidewalk and depress the freezing point by about 2 degrees C. This means that you can take something from being a sheet of ice into slush with the application of salt. It also means that seawater is harder to freeze, or it's more resistant to freezing than freshwater is. Another thing that we need to talk about is the dissolved gases in seawater. And there's a general pattern here that solubility increases with decreasing temperature. And the first gas we're going to talk about is oxygen. So there is more oxygen available in colder water because of this general pattern. What is the percentage of oxygen in air? Well, if you remember back, it's about 21%. Okay, so we've got a fairly oxygen-rich air environment on the planet. What about in seawater? It's much lower. It's 0.4% to 0.8% of the gases in water are oxygen. And that oxygen is not distributed evenly. So here I'm putting up a graphic with the tropical Pacific and tropical Atlantic defined by these curves of their oxygen. So it's the milliliters of oxygen per liter at certain depths. Tropical Pacific is the dashed line, tropical Atlantic is the bright blue line. And there's a repeating pattern. So up at the surface, there's an increase. Then we get down at about 500 meters to what's called the oxygen minimum zone. And then we see an increase in oxygen again. And I want you to think about, why is there an increase at the surface? Why is there a decrease at 500 meters? Why is there another increase down deeper? All right, you thinking about it? Okay, here we go. At the surface is where we find most of the air-water mixing. So waves, disturbance, that allows oxygen to actually get into the water. It's also where most of the photosynthesis can occur. So it's the light that's penetrating the water gets down only to a certain depth, and it's strongest right at the surface. The oxygen minimum zone, at about 500 meters, is right where photosynthesis is just about at its maximum, or just about at its maximum depth. It doesn't occur much farther down. Meanwhile, biological respiration, so the use of oxygen, is still occurring with with significance. There's still a lot of biological respiration going on. So there's no photosynthesis, no mixing, and still a lot of respiration. So it takes those oxygen levels right down. By the time we get into the true depths of the ocean, we start to see the effects of temperature. So we're getting back down into colder temperatures of water, which are holding more oxygen. There are other gases, though, we should talk about too, like carbon dioxide. And carbon dioxide comes from all sorts of places. It comes from respiration of animal life. It comes from outgassing, so it's actually being expelled into the atmosphere by volcanoes, as well as our industrial creation of, or industrial release of CO2. How much of the air is carbon dioxide? About 0.04 to 0.06% of the air is carbon dioxide. What about the oceans? Here's a graph of atmospheric carbon dioxide measured in Hawaii from about 1960 to about 2010. And what we can see here is a few things. That red squiggly line is an annual cycle lying above the major line of the blue. So that is, the line through time is the blue. The annual line with its squiggle is the red. And we can see this is an increasing amount of carbon dioxide in the atmosphere. Remember, I just said that the amount of carbon dioxide in the air is minor. But as it turns out, it's increasing. In the ocean, carbon dioxide in the ocean is 80% of the dissolved gases. Okay, we need to put this together. So why is carbon dioxide important in the ocean? Well, it reacts chemically in seawater. It's got a very high solubility. And the high levels of carbon dioxide in the seawater implies that it's never limiting regarding plant growth. Perhaps most importantly, carbon dioxide interacting with seawater creates what's called carbonic acid. And so carbonic acid can temporarily lower the pH of the oceans, making them more acidic. The normal range of ocean water is around 8 on the pH scale, from acidic to basic, right? And so the addition of carbonic acid in large amounts will decrease the pH of surface waters. This is important, and perhaps one of the most important ways in which human-induced climate change is affecting the oceans. Why? Because of shells. So a lot of organisms, a lot of marine organisms, produce shells or other external structures using what's called calcium carbonate. And calcium carbonate dissolves easily, right? So this is exactly what's going away with more acidic oceans. As calcium carbonate dissolves, it's possible to take marine species with it because it's much harder to farm shells or coral reefs or many other structures. It can take fisheries. I mean, most of your quote-unquote shellfish has some sort of calcium carbonate involved in its biology. And this could end up being entire ecosystems, right? From planktonic ecosystems to reef ecosystems. There are a lot of potential implications of increasing acidity of oceans from gases, particularly carbon dioxide, that we need to talk about. And we'll get back to them later on in the series. But that's what I wanted to cover for the introduction to the physical and chemical properties of water that are going to be important for you to understand marine biology going forward. If you have serious questions that you can't find answers to, you're welcome to come check us out. And we have a Facebook group set up for dealing with questions. It's called Marine Biology at Home. And I also wanted to say thank you very much to the folks who are helping out behind the scenes. There are lots of people working to support this lecture series, and they will either be coming up as instructors, or they're going to be helping out in the Facebook group, or they're helping to edit the lectures. So Shamar Blakeney is at Blakeney_truth at Twitter, or Shamar_Blakeney on Instagram. Dr. C is out there. She's helping out a bunch. Amy Turner is AKA Mystery on Instagram. And these folks have been tremendously helpful, so please check out their pages and social media. What is coming up next? The next lecture I've got for you on tap is Basic Oceanography. See you soon.